Hey everyone, today I want to talk about regular languages and how we can prove that a language is regular. So the first thing we need to talk about is what exactly is a language? Well, the definition of a language is a set of strings over a finite alphabet. So for example, if we have the alphabet 0, 1, which is what our assumed alphabet is going to be in pretty much every problem, because again, computers are only really reading in zeros and ones. Well, a valid language over this alphabet is the set containing 0, 0, 0, and 1, 1. This language only contains strings with characters 0 and 1. So this language is a set of strings over the alphabet 0, 1. So a language, very simply, is just a set of strings over some finite alphabet. That's all it is. Now, what exactly is a regular language? Well, let me go ahead and write this down here. A regular language is a language that is recognized by some DFA or NFA. So let me go ahead and write this down. A regular language is a language that is recognized by some DFA or NFA. So we haven't really talked about NFAs at all, so we're going to go ahead and ignore this part. But it turns out that NFAs and DFAs are equivalent, so we could just get rid of the NFA part because they're equivalent models of computation. But essentially the point is, if a language is recognized by some DFA, that language is regular. So what exactly does it mean for a language to be recognized by a DFA? Well, a language is recognized by a DFA if the DFA accepts every string in the language and rejects every string that is not in the language. So for example, let's say we have some language. Let's say it contains the strings 0 and 1. Okay, so if our DFA, some DFA that we imagine, accepts the string 0 and the string 1 and rejects everything else that's not 0 and 1, then that DFA recognizes this language. So just again to reiterate, a DFA recognizes a language if it accepts everything in the language and rejects everything that is not in the language. So that is what I mean by a regular language and what it means for a DFA to recognize a language. So this gives us a way to prove that a language is regular. If we're given some arbitrary language, we can prove that that language is regular by building a DFA that recognizes it. And that's what we're going to spend the majority of this video doing. We're going to go ahead and look at a few example languages and then build DFAs that recognize those languages. And that will go ahead and prove that the languages are regular. But first, I want to go ahead and go through some examples of some languages that you might see to sort of see the format and context of languages. Like, how are you going to see these languages? What form are they going to be in? Well, let's say we have a language that just contains the strings 0, 0, and 0, 1. So you may see a language that's written out with explicitly written out strings here, like 0, 0, and 0, 1. So it's very clear what exactly is in this language. But we could also see a language that uses set builder notation. So we could have a language of strings omega, such that omega contains an even number of zeros. So you'll notice that this language doesn't have any strings explicitly written out, but you have to sort of come to an understanding of what strings are in this language by the description or by this set builder notation. So this language contains all strings such that the string contains an even number of zeros. So when you think about what is in this language, you'll notice that this language is infinite in size. It's countably infinite, but it's infinite nonetheless, because there are an infinite number of 0, 1 strings that contain an even number of zeros. So some examples of things that are in this language are 0, 0. There are 2 zeros in this string, so it is contained in the language. The string 0, 0, 0, 0, 1 is in the language that has an even number of zeros. Any string that you can think of that has an even number of zeros will be contained in this language. And this segues me really nicely into talking about an edge case, which is the empty string. So what exactly is the empty string? Well, the empty string is the string that contains no characters, and we denote the empty string with the character epsilon. So epsilon is the empty string. And again, the empty string is the string that contains no characters. So what about epsilon? Does epsilon fit into this language? Well, it turns out that it does. Epsilon is in this language because epsilon contains 0 zeros. It contains no zeros. And since 0 is an even number, epsilon contains an even number of zeros. So it turns out that epsilon is in the language. And it turns out that epsilon is something we're going to have to be very careful about when we build DFAs. But it's also going to give us a way to sort of start off all of our DFAs, and we'll get into that when we get into the example problems. But for now, just keep in the back of your head that epsilon is going to be important because we're going to need that in basically every DFA that we build. So this is an example of sort of an arbitrary language where you kind of have to ascertain what strings are in the language based on the description. So another example of like an arbitrary language that you could see is all strings omega. Let me look at my example. All strings omega such that omega contains exactly 1, 0. So again, this is an arbitrary language of strings, so you kind of have to come to an understanding of what exactly is in this language by the description. So any string that contains exactly 1, 0 will be in this language. So for example, the string 0, 1 is in the language. The string 0, 1, 1, 1 is in the language. However, strings like 1, 1, 1 are not in the language because there's not exactly 1, 1, or sorry, 1, 0. And let's consider epsilon actually, since we were just talking about that. Is epsilon in the language? Well, it turns out that epsilon is not in this language because the string containing no characters does not have exactly 1, 0. So epsilon cannot be in this language here. So that's going to be an important question to consider for basically every language we look at, is whether or not epsilon is contained within the language. So these are some example languages that you might see that you might be asked to prove that are regular. So let's go ahead and actually get into some examples now that we know all of these terms and maybe some of the forms that these languages might come in. Okay, so our first problem, let's phrase it this way. Prove that L is regular. So L is a language where L is, okay, let's think of an example here. Let's say L is the set of strings 0, 0, and 0, 1. This is an example that we just looked at. So we want to prove that this language is regular, the language that contains the strings 0, 0, and 0, 1. So in order to do this, we need to build a DFA that recognizes the language. And again, a DFA recognizes a language if it accepts everything in the language and rejects everything that is not in the language. So we need to build a DFA that recognizes this language here to prove that L is regular. So how I was talking about in the earlier section how we can use epsilon to sort of start off all of our DFAs. So how can we do that? Well, let's first consider whether or not epsilon is in this language here. Well, epsilon is not in the language. The language contains 0, 0, and 0, 1, but it does not contain epsilon. So this sort of relates to the start state of a DFA, right? Because epsilon is going to be accepted or rejected immediately in the DFA because we haven't read in any characters. So if epsilon is not in the language, we need to have the start state be a reject state so that epsilon is not in the language. Because if we made the start state an accept state, well, no characters have been read in, so epsilon is accepted because we ended processing the string on this state here. And so if we had this state be an accept state, epsilon would be in the language, but it's not. So essentially the rule of thumb is that if epsilon is in the language, we want the start state to be an accept state. And if epsilon is not in the language, we want the start state to be a reject state. So epsilon is not in this language, so we want the start state to be a reject state. Okay, so we know how to start this DFA off using epsilon. Epsilon is not in the language, so we made the start state a reject state. Now, how do we go about sort of constructing a DFA that only accepts these strings? Well, let's just first consider what happens on the start state. What happens if we read in the character 0? Well, that's going to get us a little bit closer to a string in the language, but not quite. We don't quite have 0, 0, or 0, 1. So let's move to another state that's a reject state because we don't have these strings yet, but we're a little bit closer. We've moved closer to accepting the string. Okay, now what happens on the start state on the character 1? Well, you'll notice that no string in the language starts with a 1. So if we start out processing a 1, we know that we're always going to reject the string. So let's create another reject state down here that sort of just handles all of the strings that start with 1 because those will never be accepted. Okay, so we have a transition for each character on this state. And remember, for a DFA to be valid, we need a transition for every character on every state. So we're going to have to go and fill in transitions on all of these states here. But let's go ahead and keep moving closer to our goal here. So if we read in a 0, we're going to get a little bit closer to accepting. And if we read in a 1, we're always going to reject down here. So we've read in a 0. Now what happens when we read in another 0? Well, that's going to give us the string 0, 0. So we're going to go ahead and want to accept that. So let's go ahead and draw an arrow on 0 to the accept state. Okay, so this DFA currently accepts the string 0, 0. But what about 0, 1? Well, if we read in a 0 on the start state and we read in a 1 on this next state, we now have the string 0, 1. So we also want to accept that. So this transition is going to transition to the accept state on 0 and 1 because that's going to accept both 0, 0 and 0, 1. Perfect. So we now need to reject everything else, which we kind of handled here when the string starts with a 1. But what happens on this accept state, right? Well, if we're on this accept state, we've either read in the string 0, 0 or the string 0, 1. So if we read in any other character, we're going to get a string that is not in the language. So we're going to want to reject any string that has any other characters. So let's go ahead and route an arrow down to this reject state on both 0 and 1. Because if we're on the accept state, we either have the string 0, 0 or the string 0, 1. So any other character that is read in will give us a different string. So we're going to want to reject that in all cases. Perfect. So let's go ahead and examine our DFA really quick and see if there's any loose ends we need to tie up here. So we have a transition for each character on this state, and this state, and this state. However, we don't have any transitions for this last reject state. So let's go ahead and think about what we need to do here. So if we landed on this reject state, think about what the state of our string is. We've either started with a 1, so we're never going to accept any other string with any other characters, or we have a string that has deviated from 0, 0 or 0, 1. So we're never going to accept any other string containing any other characters. So we're going to want to loop on this reject state on all characters because the only way we got to this state is if we know that the string will be rejected for sure. And we've actually finished building our DFA here. This DFA only accepts 0, 0 and 0, 1 and rejects every other string. Thus, this DFA recognizes L, and we can therefore say thus, L is regular because we have built a DFA that accepts the language. It accepts everything, we built a DFA that recognizes the language. It accepts everything in the language and rejects everything that is not in the language. And you can go ahead and try any string you want on here. It will reject everything that's not an L and accept everything that is an L. And maybe to convince you of this a little bit more, I'll go ahead and run through a few test cases. Okay, so let's run some tests. Let's test the string 0, 0 really quick. Well, if we start at the start state, we transition on 0 to this reject state, and then we transition on 0 again to the accept state. We've finished processing our string, and we've landed on an accept state. So 0, 0 is accepted, which is what we want because 0, 0 is in the language. Okay, let's test 0, 1 and make sure it's accepted. So we start at the start state, we read in a 0 and move to this reject state. We read in a 1 and move to this accept state. We've finished processing the string, and we are on an accept state. So this string is accepted, and that's what we want because 0, 1 is in the language. And now let's test two strings that are not in the language and make sure that they're rejected. So let's test epsilon. Well, we start at the start state and we have no characters to read in, so we finish processing the string on a reject state. So epsilon is rejected. which is what we want because epsilon is not contained in the language. Perfect. Now let's consider the string 0, 1, 1. So we're going to start at the start state. We're going to transition to this other reject state on 0. We're going to transition to the accept state on 1. And then finally, we're going to take this transition to this reject state on 1. We've finished processing the string on a reject state, so this string will be rejected. And again, that's what we want because that string is not in the language. So you can go ahead and run any test you want on this DFA. It will reject any string that is not 0, 0 or 0, 1. So I think that's enough explaining for that example. We've proved that L is regular by building a DFA. So let's go ahead and try another example. So we want to prove that L is regular now, where L is equal to, and let's do like an arbitrary kind of language where it's any string with some condition. So let's test out the language of strings W such that W contains exactly 1, 0. And we already talked about this language a little bit earlier in some of my examples, but let's go ahead and prove that it's regular now. So we want to build a DFA that accepts any string that has exactly 1, 0, but rejects everything else. So remember, the first thing that we want to do in this process is consider what happens to epsilon, or the empty string. So does the empty string have exactly 1, 0? Well, it does not, so it needs to be rejected. And that means that the start state needs to be a reject state, so that epsilon is rejected. So that gives us sort of a start to our DFA here. So let's consider what happens when we read in a 0 on the start state. Well, if we read in a 0, then we have exactly 1, 0, so we want to accept that string, right? Let's go ahead and draw an arrow to the accept state on 0. So if we read in a 0 on the start state, we're going to accept because we have exactly 1, 0. Now, what happens when we read in a 1 on the start state? Well, that doesn't change anything about this condition. Reading in 3 1s doesn't get us anywhere closer to having exactly 1, 0. So we're just going to go ahead and loop on this accept state here on 1, because that doesn't say anything about our condition here. Okay, so let's consider what happens on the accept state. Well, when we read in a 0, we know we've already read in a 0 previously, so we now have more than 1, 0, which is not exactly 1, 0, so we need to reject. Now, you may be tempted to draw an arrow back to this reject state to reject it. However, notice that if we read in another 0 after that, we're going to accept the string, and that doesn't have exactly 1, 0, so we don't want that. So we're going to need to create a separate reject state that deals with that so that we don't have this sort of looping issue. So we're going to create another reject state down here on the character 0. And we're sort of going to reject any string after this because we know it can't have exactly 1, 0. Perfect. So what happens on the accept state on the character 1? Well, we know we've just read in 1, 0, so our condition is met. Any number of 1s that we read in after that doesn't change the acceptance of this condition, so we can go ahead and just loop on the accept state on 1 because that doesn't change anything. Okay, perfect. So we have a transition for every character on these two states, but we need to do the same for this last reject state here. So what happens down here? Well, if we're on this state, we know that we don't have exactly 1, 0, and we can never have exactly 1, 0 actually, because we've already read in 2 zeros, so any number of characters after this will not meet this condition. So we're going to reject for all other characters. We know that no other characters that are added can meet this condition. And this is actually the DFA. This DFA recognizes L, and therefore we can say, thus L is regular, because we've built a DFA that recognizes L. And we can go ahead and run a few tests on this one as well, just to convince you here. So let's test the string 0, 1. And notice that this should be accepted because it has exactly 1, 0. So if we start at the start state, we're going to take the transition on 0 to the accept state, and then the transition on 1 to the accept state. So we accept the string, and that is exactly what we want because that is in the language. Now what about a string that's not in the language? Let's try epsilon, for example. So epsilon is not in the language, so let's make sure that that holds. So we're going to start at the start state, and there are no characters to process, so we end on a reject state. So epsilon is rejected, which is what we want. Perfect. So let's try one more example here. Let's try 0, 0, 1. Notice that this should be rejected because there is not exactly 1, 0 in this string. So what we want to do is start at the start state. We're going to take the transition on 0 to the accept state, and then we're going to transition on 0 again to this reject state, and then we're going to transition on 1 to this reject state. So we have ended on a reject state, so we're going to reject the string, which is precisely what we want because this has 2 zeros, not 1, 0. So hopefully that's enough to convince you. You can go ahead and run some tests on your own to make sure, but this DFA recognizes L, and we've therefore proven that L is regular. So now let's run through one last example. We're going to do another language that's sort of arbitrary that you have to kind of decipher to see what exactly is in the language. So let's now consider the language of strings W such that W contains any number of zeros and ones. Okay, so let's really think through this language before we try to prove it's regular. So what strings contain any number of zeros and ones? Well, that would be any string of 0 and 1s, right? We could have 0, 0, 0, 0, 1, 1, 1, and that contains any number of zeros and ones. We could have the empty string that contains 0 zeros and 0 1s. So this is actually the language of every single string consisting of zeros and ones. So the DFA we're going to build needs to accept every string of 0, 1 combinations, including epsilon. So how might we build a DFA that recognizes this language? Well, let's consider what happens to epsilon. We know that epsilon needs to be accepted, so the start state needs to be an accept state. Perfect. Now, what happens when we read in the character 0? Well, this string, or this language, this language contains strings of any number of zeros. So if we read in a 0, we're going to accept the string because that doesn't break our condition. And what happens on the character 1? Well, the same thing, right? If we read in a 1 in any order, this condition is still met. We still have any number of zeros and ones. So this actually is going to be the entire DFA. We just need one state for this. This accepts every string of zeros and ones, including epsilon. And we can therefore conclude that L is regular. I don't really feel like we need to run that many tests, but let's just test epsilon and one other string. So is epsilon accepted? Well, we start at the start state and we take no transitions. We end on a accept state, so epsilon is accepted, which is what we want. And let's go ahead and test 1, 0, 0, 1. So we start at the start state and every transition just takes us back to the accept state. So this string is also accepted. And you can go ahead and test any string you want. This DFA will accept every string of zeros and ones, including epsilon. So that is how we can go ahead and prove that languages are regular. We need to build DFAs that recognize the language, and that will prove that the language is regular. And that's about it. See ya.